Hi everyone, my name is Joseph. Our project is reinforced generative adversarial contrastive learning for defect detection with legislation. And this is going to be a presentation on how models are developed and their output. Some of the keywords we have in this project is defect detection, generative adversarial neural network, computational vision, anomaly detection, image processing, and this contrastive learning. A brief introduction about the tire defect detection. Most of the cars are faced with accidents, and these are usually due to bad tires, overinflation, underinflation, wear and tear, poor alignment are some of the effects that we usually have. Then traditional methods that are being used for image detect for tire inspection are human based, and they are prone to errors, and these are leading to production and use of bad tires. Visual inspection, alignment check, edge inspection, and physical inspection are not really that efficient because people usually tend to miss out on some small details. They think they are minor, but they are not. So, with the implementation of advanced methods such as generative adversarial contrastive learning, computer vision, image processing, convolutional neural networks, and edge distillation, whereby a teacher model teaches a student which is a lightweight model and it's able to execute faster and produce high quality results. Then convolutional networks, which is we're using to separate between the different features of the tires, to being able to detect the anomalies. Then computer vision, capturing images in real time, and then we are able to process them so that the images are captured with high resolution and then they are fed into the system. The image processing, which is helping us to process images using data augmentation and batch processing, and then generative adversarial contrastive learning, which is taking in good images and be able to convert them to defective tires, and then teaches the system to distinguish between good and bad tires. These are the works or some of the research that has been made on this project concerning this project, and one of them is cycle guns. Cycle guns were used to produce high quality image defective high quality defective images, and this was hoping up with a generalization, and it was done by Louis in 2020. And then, although it's better than the traditional gun, but it also still faces model collapse and instability, making it difficult to generate consistent and realistic images. Then, contrastive learning. Contrastive learning has improved over time, and it's being used to distinguish between good and defective tires. And some of the research was made by Kostler in 2020. And then legislation was addressing computational limitations by compressing large deep learning models to lightweight models. And then this research was made by Tang, Hinton, and Louis in the different years, as you can see. In recent trends, machine learning has improved in this field, whereby we are having machine learning based models such as super vector machines and random forests, and these are basically handcrafted detecting defects on images, for example, edge detection and texture analysis, and they're able to classify them according to their groups. Then we also have reinforced learning, defect detection. This category can have contrastive learning and reinforced learning. So both of these are advancing well, and they're helping out with feature separation and all, and also improving. Then we have X-ray image inspection, where images tires are taken to an X-ray room, internal defect detection, and then 2D X-ray output is made, and then it is inspected to see that the tire doesn't have a defect. Then the planning models such as CNN, ResNet, and so on are being used. The problem statement and the domain problem. We can talk about the difficulty to effectively distinguish between good defective tires using traditional machine learning model. For example, the X-ray. The X-ray can leave all those hidden errors that cannot be detected, such as a slight residual change in the print. So these are also affecting For example, a high resolution image, it's affecting models like models that aren't using contrastive learning effectively. So this is becoming a problem, uh, and I hope it will be addressed. Then computational problem statement. These basically situations we face during the processing of the data, outputting results. For example, high resolution images are hard to process since they consume a lot of resources. You find that you use a lot of RAM, you use a lot of processing power to make sure you process these images fast in case the data set is very large. Then real-time processing requirements. For example, models must balance complexity and speed. So in terms when you use a hard model like CycleGAN to produce a high quality image, it will take a lot of time and yet we know the results very fast. Then large scale image data handling. So when I use it working on a large scale data set, it's usually hard to do effective processing because it takes time working through all those images in form of a loop. Then dynamic threshold and reinforced learning. Systems may likely adjust the threshold in real time while minimizing computational overhead. So in this case, I mean, in case you set the threshold to maybe say 10 images and it's able to capture about 15, can it be able to compute those 15 within in the research questions and objectives? For example, we are having questions like how can we optimize real-time processing while maintaining the accuracy, and how is computational strategies can be implemented to handle large-scale data set, high resolution images, and then how can generative adversarial networks SEGANs be used to produce high-quality images? As our objectives of our study were to optimize gun architectures to produce high quality and synthetic tires, and then to apply contrastive learning for feature separation and effectively distinguish between tires. Then we could also have noise distillation for model efficiency to ensure better generalization while minimizing computational overhead for real images. And then we also handle high resolution and large scale data sets using techniques like batch processing and data augmentation. During research, our research contribution, uh, we can say we have been able to develop hybrid models using noise distillation and different models. For example, CNN with supervised learning, uh, deep learning model with ResNet, or with convolution neural network, and then these models are being able to improve image classification. Then we are being able to implement contrastive learning technique, which has been efficient to our side, since most of our models are using it to separate good and bad tires. Then we have been able to integrate noise distillation within different models, and then it has been able to transfer knowledge that the teacher model teaches the student model, and the student model is able to classify images faster. Then we also made an advancement in computational strategies such as batch processing, the argumentation, whereby we are balancing between data argumentation and power processing to handle large data sets. Uh, then to talk about our methodology, our methodology here shows from process of where we have been generating the models and also improving our data sets. For example, we acquired images, we processed them, then we were able to visualize features using graphs. Then we extracted some of the features and then fed them into contrastive learning. And then contrastive learning was able to either feed GANs to generate new images, or use the distillation and then train the model, or just train the model after the contrastive learning, evaluate the model, and then deploy it. The dataset description. Our dataset was obtained from Mendeley, and this dataset is containing 1,856 high resolution images. So these images were the tires are grouped into good and defective tires, and this was taken different angles, different light conditions from different tire manufacturers, and this is helping out with being able to have diversity images so that our models can retrain well. So one of the models that we're able to generate is a baseline convolutional neural network model, and this the results that we retrieved from it. It's a model that is using convolutional neural networks for data processing, and it's able to abstract features using feature engineering, and then feeds the features into the convolutional neural networks, and then it's able to uh, train the model, and then save the model, and then we use ResNet 18 to push to fetch the model and be able to test it on different tires. So these are results that we achieved from the training. The training accuracy, which gradually improved from about 64 to 84. And then we also had validation accuracy, which improved from 45 to 80. And then we also had the loss on this other side, and the loss which spiked from 0.9 and 0.78 to 0.5 something, and then to 0.4. Thank you. My colleague will take on from here.
Here we have a reinforced teacher and a supervised learning model. The reinforced teacher uses contrastive learning to learn the features of the tires, and the supervised learning student will then learn these features from the teacher themselves. And we realize we plotted a teacher versus student accuracy across the epochs to know how this teacher is training the student. And as you can see, the values are at par with each other. This means that the teacher is learning efficiently and the student is learning at almost the same rate. As you can see at the end, they almost have similar results. So with this, I will give them an image samples, and as you can see, they were predicted accurately for all of them. Right here, we are looking at a VGG model, a VGG CNN model. The VGG16 is going to act as our teacher, and the CNN is a customized student who doesn't use any pre-trained mechanisms. So the VGG learns the features, and these features it trains them to the student. And as you can see in the graphs, you realize that it has a high validation accuracy. This is because it had been run before, so on its second run the validation was high. Validation accuracy shows that it can thrive through environments it hasn't been in, and towards the end, at the 10th epoch, you realize that the accuracies are actually closest to each other, which means that the teacher model was learning very well. So since the teacher model learns very well, it proves to say that the student itself will have results that are similar to that of the teacher. We created another knowledge distillation model that uses two CNN networks, and you realize that compared to the other two that used VGG and ResNet, this one seems to be having like the accuracy that is not at par with the validation. Like the training accuracy and the validation accuracy seem to be different. But the most thing we could say about this is that whenever the validation accuracy is low and the accuracy that is for training seems high, it shows that this model is overfitting. And since this teacher is overfitting, it causes the student to learn the same mistake or the same uh, characteristics, and this caused our student model to overfit as well. So that's what happened for this. Yes, so I'm going to take you through the ResNet model. Here we created a model that extracts features using ResNet, and then it identifies the images if they are good or not. From there, we have the first gradient, the FGSM. It's going to apply adversarial attacks to the images, and then the ResNet model will what? Will re-identify them, will repredict the images. Now, when you looked at our results here, you realize that the ResNet model will actually predict most of the images correctly, and from our observation here, you realize that it predicted two of them wrong. This means that our model can be used for outside, we created another model that uses random forests, but in this model we use principal component analysis to extract the features. Then it uses dimensionality reduction, and these features that have been reduced are the ones that are used to train the random forest model. We decided not to use an Adam learner of a constant rate, learning rate, so we let this model to learn by itself. And as you can see, you realize that the first accuracy was around 60%, which is good. It means that it can identify most of the features, and we realized that it didn't learn at a high rate, given that the highest accuracy we have is at 10, and at the 10th epoch, which is 57%. And when we look at the F1 score, it shows that our model is actually learning effectively, efficiently, and it's not overfitting. Yeah. We created another model using contrastive learning. Another contrastive learning model using simple framework for contrastive learning of visual representations. And while training this model, we realized that the images that came out were actually not predicted so well. It had an accuracy of around 50%. And just by looking at this confusion matrix, we realized that the true labels for the defective are 1 and the good tires are 0. Only 165 tires were predicted as good and 205 were predicted as defective. But compared to our large dataset that has 1,825 images, this is actually a poor prediction on this end. Yeah. Okay, so I'll take you through the limitations we came across while working with these models. First of all, we looked at the contrastive learning models. VG16 uses a large computing resource, so the models train for long hours, and they usually cause the computers to freeze if your PC is using those specs. Then when it comes to ResNet, unlike all the other contrastive learning models you have seen, you can convert them to grayscales, but when it comes to ResNet, you have to convert it to an RBG scale. Then when it comes to these other models, especially the guns, we realized that the models we tried to use, they didn't bring out the results we expected, even if we wanted to use them more. So we also had the dataset. The dataset had too many images, and they were having high resolutions, and it causes computational costs to our models. Now, in conclusion, our study we used an integration of psychoguns or an alternative to guns, contrastive learning, ResNet, random forests, and knowledge distillation for tyre defect detection. And yeah, moving forward, we would like to create a model that uses psychoguns for generating high quality tyre images, um, for training to reduce training instability. I would like to advance contrastive learning with reinforcement learning to create high quality models for defect classification accuracy. We recommend trying out deep convolutional networks with self-supervised learning, and we would also like to recommend implementing knowledge distillation in the models for edge deployment. Then we would like to acknowledge our lecturer, Mr. Galiwango Marvin, for giving us guidance when it comes to this project. I would like to acknowledge all the researchers who have tried their hand at defect detection models. Thank you very much. We also like to thank our families for helping us and supporting us throughout this course.